Welcome back, and here we're going to consider another problem where we're looking for a range, okay? And in this case, we're looking for the range from the exhaust port of the Death Star that R2-D2 is going to calculate for releasing the bomb. So the bomb will just go right into the exhaust port and blow up the Death Star, and everybody will be happy. Okay. Now, obviously, Luke Skywalker uses the Force in the first version of this alternate reality, but this is physics class, so physics it is. Now, the one thing that you would expect to change for a projectile like this on the Death Star versus here on Earth is the value of G, okay? And when I was setting up for this problem, I thought, well, let's see if we can calculate G for the Death Star. And they don't have these things recorded, surprisingly. But they do have things like what the mass of the Death Star is meant to be and size. You can look all this up on a place on the internet called Wikipedia. Hilarious. And when you do the calculation, you find that G for the Death Star is a mere 0.02 meters per second squared, okay? So 2 centimeters per second. What to compare that to? If you were to drop something on the surface of the Death Star, then it'd be like watching here on Earth a pebble fall through a, vat of corn syrup or something like that, really slowly, okay? So that's going to change things considerably in our calculation, but otherwise everything stays the same. We're talking about the Death Star, which is, planet-like. And so all the rest of the bits and pieces work very nicely. Now, let's get ourselves a nice diagram of this situation. There's Luke's X-Wing. I wonder if I'm committing copyright infringement here. We'll see if this gets flagged on YouTube by a super aggro lawyer, courtesy of the mouse. But in any case, X-Wing graphic may change in a future version of this video that doesn't get banned. Fair use, right? Anyway, we have a little diagram here. We want to indicate, okay, well then what is delta X? There's our exhaust port where we want the bomb to end up. We're given the initial velocity of the X-Wing, which of course is the initial velocity of the bomb that it drops, because the bomb is coming along with the X-Wing until it gets dropped. And we have some delta Y that it falls through before it gets to the exhaust port. As we will find, this drawing is very far from being properly to scale, but I've noted some of the things that we already know about this situation over here. All right. Now, I say in the problem, and this is often done, is their velocity is horizontal, okay? And what I've done is translated that into vector land here, okay? And what furthermore that tells us is that the x component of the initial velocity is the whole vector, right? Because it's horizontal, okay? And it also tells us that if the whole thing is in the x direction, well then the y component, the vertical component to its initial velocity, is just 0, okay? As we will see, that considerably simplifies the calculation we're about to do. Now, if you're looking at this and you're thinking about the last example that we did in a previous video that allowed us to calculate range, we might say, oh, we have an equation for range, Dr. Fairbanks. This is really simple. I've got initial velocity, I've got G, and I'm just going to plug some things in there. I don't know, an angle, and it's going to come out, and I'm going to write down that number. Just stop it, okay? Stop it right now. Don't be that silly. You know that's silly, because the thing I shouted in that video, said with emphasis, I suppose, is that that's for level ground. We're no longer on level ground, right? We're starting from a vertical position. We're going to a completely different vertical position. We can't use that range equation. We have to do something else, all right? So don't you dare. Okay. As before, though, it's best to go right at the solution if we can. So let me see if I can grab a different color. Let's calculate delta x. Let's do it. Just write it down. And we find ourselves stymied in the exact same spot as we were last time. We know this thing, we want this thing, but we also don't know the time of flight. So we need to go get the time of flight. There's no way to do it just using the characteristics of the bomb's horizontal motion. And so we need to appeal to its vertical motion and what we know about that to figure out how long it takes to fall through this 50 meters of displacement from where it's released to where it enters the exhaust port, then to blow up the Death Star. So if you look at the vertical equations of motion, you look down the list and you'll see that we don't know the final y velocity, and most of the equations of motion involve the final vertical velocity, so the y component of the final velocity, except for one. And it's exactly the same equation of motion that we used in the last example, but it's going to look very different here, okay, for a couple of different reasons. Okay, but we're still looking for time. This is a time equation that doesn't involve the final velocity in the y direction, and so it's the shortest route we can take. Now, if you're looking at the form of that thing and you're saying, oh, well, delta y isn't 0, so that doesn't simplify it. And so we've got a quadratic, Dr. Fairbanks, and we have to break out the quadratic equation. Well, one, that shouldn't be that intimidating to you. But two, we don't actually have to do that again. And the reason we don't have to do that is because the initial vertical velocity is 0. It's released when the X-wing is moving at a level velocity, right? Horizontal along the surface of the Death Star. So this term drops out of the equation because that bit of it is 0. And that makes solving for the time here pretty straightforward. We multiply both sides by 2. We divide both sides by the vertical acceleration, and we get that t squared is equal to that, which means if we take the square root, then we get what we want. We'll get an expression for time. Now, a few things here. One, it's important to realize that no, we won't be taking the root of a negative number because delta y and the vertical acceleration here are both downward, so they're both going to be negative, and so the negative signs cancel, and we should be okay on that front. The other thing is that now that we're on a different planet, quote unquote, and you're used to maybe plugging in downward 9.8 meters per second squared for the acceleration, well, remember, we're somewhere else in an alternate reality, and so we need to put in the appropriate value of g when we plug and chug here. If you do that, what you should come out to is a time of 70.71 seconds. I'm keeping some precision here so that we don't round too much before going to a final answer. That's a long time to drop 50 meters. On Earth, it takes a couple of seconds to do that. When your value of g, however, is so much smaller, right? Let's see, how many times smaller? It's like 500 times smaller than Earth's value. Well, then it takes a lot longer to drop through 50 meters. But it does happen eventually. The knock-on effect of that is that when you take this number for time of flight and you put it in here to then calculate successfully our delta x, well, then delta x is 450 meters per second for the initial horizontal velocity times 70.71 seconds for the time of flight. And so the delta x for this problem comes out to about 31,820 meters. Okay, couple of things. If you try this problem again and you assume that R2D2's altimeter is out of calibration by, say, a centimeter, like just that decimal place right there, okay? Well, then he'll miss the exhaust port, assuming the exhaust port is about the size that it is in the movie, and, well, that won't go well for the rebels. But because such tiny differences, because the time is so large, that will affect this result by, a few meters or something like that and miss the exhaust port. Okay, so there's definitely a precision issue here. We better hope his altimeter is really good and his measurements of Death Star's G is also really good, and also that the measurement of this velocity is really good, or we'll miss the target. The other thing here is this is 31.82 kilometers. It's probably beyond the horizon of the Death Star, so unless R2-D2 has some quite fancy sensors, this is unlikely to meet with success. It's probably best that Luke Skywalker used the Force on this one, and maybe they did this calculation. That's the way they wrote the movie. I'm sure that's what happened. Okay, so there's one more example where we used exactly the same equations of motion, right? We started in exactly the same place in the horizontal and vertical directions, and yet things looked very different given the situation that we applied them to. All right? I hope the process here is relatively clear. Hope it helps you solve out some of these projectile motion problems on your own, and I'll be seeing you. Bye.